Hey folks, I hope you're doing well today. We want to talk about the natural exponential function today. We'll talk about the derivative of this function and the integral of this function. But first, we got a definition. The inverse function of the natural logarithmic function, and you remember the natural logarithmic function, remember the definition we gave a couple of sections ago, is called the natural exponential function, and you've seen it before. It's denoted as f inverse of x, where f of x is natural log of x, of course, is e to the x power. So remember, this is exponential form, whereas if we rewrite that, that is logarithmic form for the same equation. But e to the x and natural log of x are inverse functions of each other. So to start off, I would like to give a couple of equations. You have solved equations like this before in a pre-calculus algebra class. But notice our first example A, we have natural log of the entire argument 2x is equal to 12. So my goal is to isolate this x. Well, to isolate this x, I have to remove the natural log function in front, and to do that is to use its inverse. And so what this is called is exponentiate both sides. So I'm going to say e, and then I'm going to move the natural log of 2x up to an exponent equals e to the 12th. And again, that idea is called exponentiating both sides. Now the reason I do this is because you remember e and natural log are inverses of each other. So the e and the natural log cancel each other out, and then I have 2x, which is now normal level, is equal to e to the 12th. And to solve for x, I'm going to divide each side of the equation by 2. So my exact answer is e to the 12th divided by 2. It would help to have an approximation there, so I'm going to type that in my calculator. Get 81,377. I guess we need to pick up placed around. Let's go out 2 places, so that would be 0.40. So a large number. This value to me is more telling, but if you were doing a word problem and that was your result, you want to know how big that actually is. So there is that equation solved. Be sure when you type in e to the 12th in your calculator, for a lot of calculators a parenthesis will pop up here, so before you divide by 2 you need to close that parenthesis out to get the correct answer. Now, the next equation that I want you to solve, B, right here, notice this is an exponential equation. So your first equation was a logarithmic equation because it has a natural log within the equation. This, on the other hand, is an exponential equation because your variable is up here as an exponent. But it is a base e, and so to get rid of the base e so we can isolate the x value, we're going to evaluate the natural log of both sides. In other words, the inverse of base e. So I have the natural log of e to the 2x power is equal to the natural log of 5. Now, why did I do that? So this natural log and e, they're inverses of each other, will cancel each other out, and I get 2x, now normal level, not an exponent anymore, is equal to the natural log of 5. And to solve for x, I'm going to divide each side of the equation by 2, and I get my exact answer of natural log of 5 divided by 2. And if you needed a decimal approximation of that, you type in natural log, or the capital LN in most people's calculator. Once again, a parenthesis pops up right here. So you type in, of course, your 5, but make sure you close that parenthesis out before you divide by 2. And I get 0.8047. I'm just taking this out 4 decimal places because that's where I decided to take it out just right now. Hopefully there'll be directions that go along if you're asked to find a decimal approximation of your result. Next, I'd like to give you a list of properties of the natural exponential function. Again, keep in mind the natural exponential function is the inverse function of the natural logarithm function. So the domain would be the range of the logarithm function, and the logarithm function has a range of negative infinity to infinity, so that turns into the domain. whereas the range of an inverse function is the domain of the natural log, which is 0 to infinity, so that is now the range, okay? Property 2, the function f of x equals e to the x is a continuous function. The function is increasing because its inverse is increasing. Remember, we had that property in the inverse functions, and is one-to-one because the original function, which is the natural log of x, is a one-to-one function. Property 3, the graph of f of x equals e to the x is concave upward on its entire domain. Now, I believe each of you have probably seen the graph of e to the x before, but one important point, because it is the inverse of the logarithm function. First, let me do a quick sketch of the logarithm function. Okay, so this is a quick version of y equals natural log of x. And remember, the inverse is a reflection through the line y equals x. So the inverse in green, e to the x, is going to look very similar to that. Notice this point right here, which was 1, 0, turns into 0, 1, and then every other point also switches x's and y's. And you can see from here that the green graph is a continuous function. It's increasing, it's one-to-one, and it's concave upward. Property 4, the limit as x goes to negative infinity of e to the x is equal to 0. If I go back to my quick sketch on the previous page, notice as we go out to negative infinity, the line is approaching 0, which means we have a horizontal asymptote, right? On the other hand, if we go to positive infinity, the limit is infinity. So I'll go back and look at my green graph. As I go out to the right forever, my green graph goes up forever. And then we have another theorem. It says let u be a differentiable function of x, then the derivative of e to the x, you're going to love this, is e to the x. It's the only function that I am aware of that the derivative is identical to the original function. It's really neat. Okay, and the derivative, if you're doing like a chain rule problem, this is what this is, the derivative of e to the u. So say you have something other than just x as your exponent, then it is going to be e to the u times the derivative of the exponent. So what I'd like to do is do several problems where we take the derivative. That's the ultimate goal in this section, is to take the derivative of e to the x. And so find the derivative of the following. So I have f primed of x. Now keep in mind the derivative of e to the x is always e to the x. If you have something other than x as your exponent, you're going to use the chain rule. So when you use the chain rule, you rewrite the original function times the derivative of the exponent. And the derivative of 1 minus x, well, we know the derivative of 1 is 0, and the derivative of minus x, or negative x, is negative 1. Now, I want to simplify that just so it looks better. The negative 1 I'm going to multiply in front, so negative 1e to the 1 minus x, which could also be written as negative e to the 1 minus x. And that is your first derivative of that exponential function. Next example, notice again, I have e to the x. Okay, so the derivative of e to the x is e to the x, except when you have something other than x as your exponent, and you're going to take that, the derivative, you're going to take the derivative of the exponent and multiply times your e to the u. So the derivative of negative x squared is negative 2x. It looks better if I pull that product in front, so negative 2x e to the negative x squared is your final simplified result. So you get it, the derivative of e to the x is e to the x. And if you have something other than x as an exponent, you have to multiply times the derivative of that exponent. So let's keep this process going. So y equals x squared times e to the negative x. So this is a product rule problem, right? So remember, first times the derivative of the second, plus the second times the derivative of the first. And when we take the derivative of the e to the negative x, we will use again the chain rule. So it'll be e to the negative x times the derivative of the exponent. So let's get started. So y primed equals the first, which is x squared. So first times the derivative of the second. So the derivative of e to the negative x is e to the negative x times the derivative of the exponent, which is negative 1. Plus, now we write the second, right, which is e to the negative x, times the derivative of the first, which is 2x. So folks, that's our derivative, but we need to write it simplified. So y primed equals, now this negative 1 being multiplied at the end of that first term, I'm going to put it in front. So how about negative x squared e to the negative x, and then plus, and I think it looks better with your e's in the back, so I'm going to put 2x in front, e to the negative x. Now this suffices as an answer, but I'm going to promise you, you're going to see that factored. So look what's in common. Notice both these terms have an x in common, and they have an e to the negative x in common. So we could pull that out. So x, e to the negative x comes front. Now I pulled out one of these x's. The negative still remains, so negative x. And then all that remains here when I pull out x e to the negative x is plus 2. You also might see that as x e to the negative x instead of negative x plus 2, 2 minus x. Or somebody else might pull out the negative with the factor in the front. But that's just more of an opinion than anything else. Okay, our next problem. What do we do with this? So the derivative of natural log, remember we talked about that a section ago, or two ago, but the derivative of natural log is 1 over what's on the inside times the derivative of the inside. But we also know that if we can simplify our natural log, in other words, if we have multiplication or division or an exponent inside, we can simplify that expression. So that's my advice. I'm not taking the derivative yet, although I'm trying to write it that way. There we go. Then I can split this up into subtraction. That'd be the natural log of 1 plus e to the x minus the natural log of 1 minus e to the x, right? So I use the quotient rule, not for derivatives, but for natural logarithms. Now what I'm going to do is take the derivative of each of these terms separately. So we'll take the derivative of that, separate then the derivative of that, and then subtract. So I have y primed equals, now again, to remind you, the derivative of natural log is 1 over the inside times the derivative of the inside. So the derivative of 1 is 0, and the derivative of e to the x we know is e to the x. So the derivative of this first term is completed. Minus 1 over the inside again, right? 1 minus e to the x, and then times the derivative of the inside. So the derivative of 1 is 0, and the derivative of minus e to the x is minus e to the x. Now I had to put parentheses there because if I don't, it looks like I'm doing 1 minus e to the x, and that's a multiplication issue there. Now if I write this a little more simplified, I could put this e to the x in the numerator, so there'd be e to the x over 1 plus e to the x minus, now this minus and this minus, because this is multiplication, turn into plus, and then that would be e to the x over 1 minus e to the x. You could find a common denominator and combine those together. I don't know if that's worth it or not. I'm out of space, so I'm just going to skip that option. I think that is a reasonable answer though. So E, I have another derivative problem for you. It looks like we might need to jump into the quotient rule, right? Because we're dividing. But fact is, I could just split this up into two separate fractions. So I'm rewriting this problem. Y equals, what if we did e to the x over 2 minus e to the negative x over 2? Or you could even say that's y equals 1/2 e to the x minus 1/2 e to the negative x. Notice I haven't taken a derivative, I've just rewritten my equation or my expression. This, I think, is the easiest, the bottom one, to take the derivative of, because the 1/2 is just a constant multiple, so is the negative 1/2. So I have y primed equals, again, I just bring down my constant, and then the derivative of e to the x is e to the x. And then for the second term, I have minus 1/2. Now the derivative of e to the negative x is e to the negative x, but see, I don't have just an x in the numerator, so I have to take the derivative, not the numerator, the exponent. I have to take the derivative of the exponent, so times negative 1. And what is that negative 1 going to do? Well, let's move it in front, and that's going to change that to a plus. So the final result, how about 1/2 e to the x plus 1/2 e to the negative x. You could even factor out that common 1/2, but I don't think that's necessary. If we did, it would look like this, e to the x plus e to the negative x. So either one of those answers is perfectly fine. So for example F, we have a fun problem. This is implicit differentiation. Remember, implicit differentiation applies when you have x's and y's implicit in your equation. Okay, you can't solve for y explicitly. Remember, explicit equation is when you can isolate the y. We can't easily do that. The y is all mixed up. So the rule is when you differentiate implicitly, when you take the derivative of y, you have to write times dy over dx. Or you'll see some books write times y primed. I'm going to go ahead and put dy over dx because I think it's just easier to look at. So when I take the derivative of e to the x, well, e to the x times y, right? It's just going to be e to the x times y, but then I have to multiply that times the derivative of the exponent. Well, that's a product, right? We have to use the product rule when we're using the chain rule for this exponent. So I'm going to say first times the derivative of the second. Well, the derivative of y is 1, but since I took the derivative of y, I have to put times dy over dx. Plus the second, which is y, times the derivative of the first, which is which is 1. My apologies. X is the first, but the derivative of that is 1. Okay? So again, first, this is just for this exponent. So first times the derivative of the second, which is 1 dy over dx, plus the second, which is y, times the derivative of the first, which is 1. Okay? Now I'm moving over to my second term, which is just x squared. The derivative of x squared is just 2x. And then the derivative of y squared is just 2y, but since I'm taking the derivative of y, I have to put times dy over dx. Okay? And then on the other side, the derivative of 10 is 0. So this is where we are. So make sure you follow that before we do anything else. Now remember, the next goal is to solve for our dy over dx. Now to do that, I'm going to have to get all my dy over dx terms to one side of the equation, which means I'm going to have to do something with the set of parentheses right here. So I'm going to distribute, watch this, I'm going to distribute this e to the xy inside my parentheses here, okay? So I'm going to have x e to the xy times dy over dx plus y e to the xy plus 2x minus 2y dy over dx, and that still equals 0. Now what I have here is I have a dy over dx term here and a dy over dx term here. I'm going to leave those two guys on the left side of the equation, and then I'm going to move the terms that don't have a dy over dx as a factor onto the other side of the equation. So now I have x e to the xy dy over dx minus 2y dy over dx. On the other side, now I have negative y e to the xy minus 2x. You follow that? So those two guys not highlighted go to the other side. On the left, I'm going to factor out my dy over dx. That's going to leave x e to the xy minus 2y. And on the right, I'm writing exactly what I had in the line above. My final answer is going to be to divide both sides of my equation by this x e to the xy minus 2y. So I get a final answer of dy over dx is equal to negative y e to the xy minus 2x, which was already in the numerator on the right, and now in blue, what's below it in my denominator, x e to the xy minus 2y. You would look to see if you could simplify anything there. I'm not seeing anything. Make sure your x's look like x's and y's look like y's. Notice I'm struggling with that a little bit. And I think that's about as simple as that gets. And there we go. And for example, G, we have a second derivative problem. you might want to pause this one and try this on your own. Of course, you know a second derivative is simply the derivative of the first derivative. So this may even take more than my single page that I have here, but I'm going to try to be neat and get it all on one page. But pause it, see if you can do it. So here we go. We've got g primed of x is equal to. Now, first of all, you know, square root of x, we could write that as x to the 1/2. So let's assume I've already done that. So when I take the derivative of x to the 1/2, it'll be 1/2 x to the negative 1/2, just using the power rule, right? But now, e to the x times natural log of x, that's a product rule. So I'm going to do, remember, first, which is just e to the x, times the derivative of the second. The derivative of natural log of x, remember, is 1 over x, plus the second, which is natural log of x, times the derivative of the first, which is awesome. The derivative of e to the x is just e to the x. Isn't that great? Now your next step, maybe you want to simplify this as much as you possibly can. I don't see that, y'all, that there's a whole lot we can do. Probably that middle term, like 1/2 x to the negative 1/2, it's worth leaving as is. But the middle term, you might want to write that as e to the x over x, and then plus natural log of x times e to the x, I think is as good as that gets. Now, I think I'm going to do my second derivative. Let's try that in orange, okay, just so you can follow when you look back at this. So the second derivative, g double primed of x. So I'm just doing this term by term. Notice we have 3 terms here. I'm going to take the derivative of that, separately the derivative of that, and separately the derivative of that one. So the derivative of 1/2 x e to the negative 1/2, that is a negative up there, is going to be, again, the 1/2 is a constant multiple. And then I move my negative 1/2 in front, so times a negative 1/2 x to the negative. Now 1/2 minus 1 is going to give us negative 3/2. We'll clean that up in a minute. Now when I move on to my second term, I need the quotient rule. So I'm saying the bottom, or low, d high, the derivative of the top is e to the x, minus high, which is e to the x, and then d low, which is going to be 1 all over, don't forget, the denominator squared. Now, you could have used the product rule, too, and take the x to the top and make it x to the negative 1. That would work as well, but I tend to just use the quotient rule when I have a quotient. Now, here I'm going to use the product rule. So it's going to be plus first, which is natural log of x, times the derivative of the second, which is e to the x, plus the second, which is e to the x, times the derivative of the first, which is 1 over x. Now the idea is maybe simplify this expression as much as we possibly can. So that's my derivative. It just looks awful. So here we go. This 1/2 times the negative 1/2 is going to be negative 1/4. And then this x to the negative 3/2, I could take that to the denominator. So I would have negative 1 over 4. And then that would be x to the 3/2. If we need to do anything else with it in a minute, we will. And then this is plus. Here I'm going to leave as is for now, x e to the x minus e to the x all over x squared. And then over here, natural log of x times e to the x plus e to the x over x. Now I do see that we might could simplify this just a little bit. Notice at the end I have this e to the x over x term, and I would also have an e to the x over x right here if I would split this up into 2 separate fractions. So I'm going to split that up. Okay, so it does clean up a little bit. So in green I'm going to clean it up. I've got negative 1 over 4. Again, you can write that as x to the 3/2, or you can write it as the square root of x to the 3rd. All right, plus, now this first circle here, x over e to the x over x squared. So x, I said that wrong, e to the x over x squared. We'll simplify that in a minute. Minus e to the x over x squared plus natural log of x e to the x, and at the end plus e to the x over x. Now, fact is, right here, that is an e to the x over x. Do you see it? This x cancels with one of those. So final result, probably as good as it gets, is negative 1 over 4 square root of x to the 3rd. And then this e to the x over x plus this e to the x over x is going to be plus 2 e to the x over x minus e to the x over x squared plus natural log of x times e to the x. There is your second derivative. I think I'm going to go ahead and wrap up this video because next we're going to talk about integration. So I'll do a quick video when you return, part 2, about the natural exponential function, talking about integration. Hope you have a great day.